Welcome to the session on hypothesis testing, two-tailed tests. The objectives for this session are to carry out and interpret a two-tailed test for the proportion of the binomial distribution. Recall that we use a one-tailed test when there is a claim that probability has either gone up or gone down. A two-tailed test is used when it has been claimed that the probability has changed in either direction. For a two-tailed test, halve the significance level at the end that is being tested. For example, if the test statistic is x distributed binomially, then the expected outcome is NP, where n is the number of trials and p is the probability. If the observed value x is lower, then consider probability of x less than or equal to little x. And if it is higher, then consider probability of x greater than or equal to little x. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Over a lengthy period of time, it has been found that the noodle bar has a ratio of non-student to student customers 1:3. In the pizza place, in a random sample of 15 people ordering, 3 were students. Using a 5% level of significance, test whether or not the proportion of students in the noodle bar is different to that in the pizza place. So the first question we should ask ourselves is, which test should we use? The key words in this example are is different to. Therefore, we need to use a two-tailed test. Other keywords in this example have now been highlighted in red. The proportion of students at the noodle bar is 0.75 or 3 out of 4. We have gathered this from the fact that the noodle bar has a ratio of non-student to student customers 1:3. We let x be the number of students in the sample from the pizza place and let p be the probability that a randomly chosen person in the sample from the pizza place is a student. The null hypothesis is p equals 0.75 and the alternative hypothesis, H1, is p not equal to 0.75. So this is where we get the 0.75 from. It's the proportion of students at the noodle bar. And this is what we're testing for. We're testing to see if the number of students or the proportion of students in the noodle bar is different to that in the pizza place. So if H0 is true, or the null hypothesis is true, then x is distributed binomially with n equal to 15 and p equal to 0.75. We have a sample of 15 people and a proportion of 0.75. That's the number of students or the proportion of students at the noodle bar. So the expected value is n times p. So 15 times 0.75, which is equal to 11.25. The probability that x is less than or equal to 3 is equal to probability that x equals 0 plus probability x equals 1 plus probability x equals 2 plus probability x equals 3. And we can calculate this using the formula for the binomial distribution, as shown here. So here's the probability for x equals 0, and for x equals 1, for x equals 2, and for x equals 3. Of course, we've simply applied the formula at the bottom of the screen. And so the probability that x is less than or equal to 3 is equal to 0.0000124 to 3 significant figures. Alternatively, we could have typed in Excel equals binom.dist, open bracket, 3 for little x, positioned here and here, n equals 15, positioned here, and p equal to 0.75, positioned here. This is less than 0.025. And of course, we've used 0.025 because it's half of the 5% significance level that we're required to consider. So there is evidence at the 5% level to reject H0 in favour of H1. So therefore, there is evidence to suggest that the proportion of students at both outlets is different. Now let's consider a second method for solving this example. The first few lines of our solution will remain the same. So the proportion of students at the noodle bar is 0.75, or 3 out of 4. And we let x be the number of students in the sample from the pizza place, and let p be the probability that a randomly chosen person in the sample from the pizza place is a student. H0 remains as p equals 0.75, and H1 remains p not equal to 0.75. So if H0 is true, then x is distributed binomially with n equal to 15 and p equal to 0.75. So up to this point, the two methods are exactly the same. However, beyond this, we use a different approach for method 2. We are going to find the critical regions by finding the two critical values, as this is a two-tailed test. If our test statistic lies in the critical region, then we reject H0 in favour of H1, otherwise we do not reject it. So, let C1 and C2 be the two critical values such that probability of x being less than or equal to C1 is less than or equal to 0.025, and probability that x is greater than or equal to C2 is less than or equal to 0.025. And of course, we've used 0.025 because we're considering the 5% significance level, and 0.025 is half of 5%. Let's consider C2 first. We're going to use Excel to help us with our calculations. However, you can use a calculator or a hand technique. We've been through this in previous sessions in more detail, and we may go through this a little bit quickly, but the method is there for you to use if you wish to do so. If you find it too complicated, use method 1 instead. So remember in Excel, in order to find the smallest r with the probability that x is greater than or equal to r is less than alpha, for x distributed binomially, open bracket n comma p, we type binom, or rather equals binom.inv, open bracket n comma p comma 1 minus alpha, then add 1. So in our example, we type equals binom.inv, open bracket, n equals 15, comma p equals 0.75, comma 1 minus alpha equals 1 minus 0.025. This gives us 14, and of course we add 1 at the end in order to find this critical value C2. So C2 equals 15. So the probability that x is greater than or equal to 15 is less than or equal to 0.025. And 15 is the smallest value which satisfies this. And now for the other inequality. Let C1 be the critical value such that probability of x less than or equal to C1 is less than or equal to 0.025. In Excel, in order to find the largest R with probability x less than or equal to R less than alpha for x distributed binomially, we type equals binom.inv open bracket n comma p comma alpha. So in our example, we type equals binom.inv open bracket n equals 15, p equals 0.75, and alpha equals 0.025. And this gives us the value 6. So C1 is equal to 6. So we have that C1 equals 6 and C2 equals 15. And the critical regions are probability x less than or equal to 6 is less than or equal to 0.025, and probability x greater than or equal to 15 is less than or equal to 0.025. Now, we know that there were 3 students in our sample, and so since the observed value 3 lies in the critical region, we reject H0 in favour of H1. And so there is evidence to suggest that the proportion of students at both outlets is different. This brings us to the end of this session. If you have understood its contents, you should be able to carry out and interpret a two-tailed test for the proportion of the binomial distribution. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.